This video is going to cover the concepts for section 3.4, and then the following videos will deal with actual examples. And so there's a good bit of concepts for section 3.4, and I'll start with the concept of concavity. Concavity deals with the sort of the shape of the graph of the function. And in this diagram or this picture, I have this green curve, that's the graph of the function. And you'll notice for this first portion, it's called, I have the words concave down. And it's got this hump, and it's essentially opening downward, is how you would say. And that's called concave down. And then the second portion, it's opening upward, and that's called concave up. And then you'll see in red, and it's F, and then looks like 2 quotation marks, and then X greater than 0. This is the second derivative. So it's saying the second derivative of the function is greater than 0. And that happens when it's concave up. And you would pronounce it as F double prime of X for the second derivative. And in other words, the second derivative is positive when it's concave up. And then for the portion where it's opening downward, for the concave down, you'll see F double prime of X less than 0 in red. So that's saying the second derivative of the function is negative when the graph is concave down. All right, so that's visually what we're dealing with. And in relation to the second derivative, positive second derivative is concave up, negative second derivative is concave down. Now, specific definitions, f of x is concave upward on some open interval I if its first derivative is increasing. And I put in yellow, in other words, its second derivative is positive. So we know from previous section when we dealt with finding the intervals of increasing and decreasing, the function's increasing if its first derivative is positive. Now we're dealing with the derivative of the first derivative. That's what the second derivative is. So if we consider the derivative f prime of x as our function, we look for where that part is increasing. And that happens when its second derivative, f double prime of x, is positive, because that second derivative is the derivative of the first derivative. Similar, concave downward is on an open interval I is when its first derivative is decreasing. In other words, the second derivative is negative. All right, so the graph of the derivative is decreasing. That means it's going to be concave downward, and that also translates into just saying the second derivative is negative. All right, so that's the concept of, or just some terminology of concave up, concave down, and its relation to the second derivative. Essentially, the graph is opening downward or concave downward. If its second derivative is negative, it's concave upward. If its second derivative is positive. And then I said note, f double prime of x is the second derivative of f of x. It is the derivative of f prime of x. So it's the derivative of the first derivative. All right, so there's a theorem in the textbook that deals with tests for concavity. And it says let f be a function whose second derivative exists on some open interval I. And this just reinforces what we're talking about. The first case is if its f double prime of x is greater than 0. So the second derivative is greater than 0. The graph of f of x is concave up. All right, so the second derivative is positive, concave upward, which I've already talked about in this picture. And second condition, if the second derivative is less than 0, For all x in the interval, it's concave downward. In other words, the second derivative is negative. And then this third condition, third scenario, is if the second derivative equals 0 for all x in some interval. That's going to be a graph for f is linear. So it's basically the graph of f is a line. Okay, and I've already talked about that, so that theorem pretty much reinforces what I have in this picture. Concave up, second derivative is positive. Concave down, second derivative is negative. All right, so now moving on to what's called an inflection point. And I abbreviate it as IP. So it's going to say let f of x be continuous on some open interval I, and let x star, so this is my notation. You'll see the letter C in the textbook, but I wanted to use a different notation for inflection point so that we don't confuse it with critical number, because the textbook also uses the letter C for critical number. So I'm using x star for inflection point. So let x star be some point on this interval. If the graph of f of x has a tangent line at x star, or the point x star comma f of x star, then this point is a point of inflection of the graph of f of x when the concavity changes from upward to downward, or vice versa, or downward to upward, which switches concavity is what a point of inflection is. It's the point, where it switches concavity, and I'm calling that x star for where the x coordinate is of that point. All right, and something important is that this requires the tangent line to exist at the inflection point, and that is specific for this textbook only. Other textbooks do not require that the tangent line existing at the inflection point, but we're dealing with it having to exist. So graphically, this is representing inflection point. So we have the first portion, the graph's opening upward, so it's concave up. And then the second portion, it's opening downwards, concave down. And you'll see the inflection points midway between these two areas. And that's where it switches concavity, so concave up to concave down. And that's the yellow dot. And again, I'm abbreviating or representing it as x star for the inflection point. All right, so inflection point is just the point in which the graph switches concavity. All right, so theorem 3.8 is dealing with the inflection point. So if x star comma f of x star is an inflection point or point of inflection, then either the second derivative at x star equals 0, or the second derivative does not exist at x star. All right, so it's either equal to 0 or does not exist, and it's dealing with the second derivative. All right, so that's why I'll make a comment in yellow, is that we do not confuse this with a critical number. And again, I said this earlier, I use x star for the inflection point to distinguish it from a critical number. The textbook uses the letter C for both. And so I wrote down, recall from section 3.1, if the first derivative of C equals 0, or if the first derivative of C does not exist, then C is a critical number, or the point C comma f of C is a critical point. So it's very similar definitions. It's just inflection point, you have the second derivative equaling 0, or a second derivative does not exist, where the critical number, you have the first derivative is equal to 0, the first derivative does not exist. All right, so that's an important distinction between the two. Some people in the past, when I taught this course, confuse them, and so do not have those mixed up. They're two separate things. So this leads to the last thing, or theorem, or idea for this section. It's the second derivative test. And it says that you have a function f of x such that its first derivative at c equals 0, and the second derivative of the function exists on some open interval containing c. So the condition is we need its first derivative of c to equal 0. So that's, in other words, that's a critical number, right? Because if its first derivative of c equals 0, that just means that c is a critical number. All right. Now we needed this added thing is that the second derivative exists on an interval containing this critical number. You have three cases. If the second derivative of c is positive or greater than 0, then you have a relative min at the critical number c comma f of c. If the second derivative is less than 0 or negative, then you have a relative max at the critical number c comma f of c. Now the third case, if the second derivative of c is 0, the test fails, and you might have to apply the first derivative test. All right, so this is what the second derivative test says. And notice it's similar to the first derivative test in the sense that you're determining a relative min or a relative max. They both incorporate that central, I guess, idea, determining the min or max to the graph. It's just for second derivative test. Notice there's no mention of forming any intervals of increasing and decreasing, whereas the first derivative test, you had to form intervals of increasing and decreasing. All you do for the second derivative test is, okay, first determine your critical number, and it's got to be a critical number in which the first derivative is 0. All right, that's crucial. We don't deal with any first derivative of c not existing. Okay, so it's got to be particular to which its derivative is 0. All right, and then the second derivative exists on some interval of some range of values that contain c. All right, and to reiterate, you have the three scenarios. It's either the second derivative at the critical number is positive, then you have a relative min for the critical number. Or if you have the second derivative for the critical number is negative, then you have a relative max at the critical number. And then if it's equal to 0 for the second derivative, the test fails. And it might not be a relative min or a relative max. You would have to use the first derivative test to conclude that. So I drew a graph, and this kind of shows the scenarios. I have this point C1, and notice at C1, you have a relative max. All right, so that's a relative max at C1. And notice I wrote in purple, it's concave down. So the graph is opening downward at C1. And if it's concave down, that means its second derivative is negative. So that's why it says f double prime of C1 is less than 0. All right, so that's the second derivative part of the definition, is that it's concave downward if the second derivative is negative. Now notice I drew this red dashed line, and that's a horizontal tangent line. All right, and the horizontal tangent line is has a slope of 0. In other words, the first derivative, f prime of C1 equals 0. So that's where you have a horizontal tangent line at the relative max. And then also the graph is opening downward. So its second derivative is negative. The other point, C2, this is a relative min, and it's opening upward. So it's concave up. And that means its second derivative for C2 is greater than 0. So that's positive for the second derivative. And you also have a horizontal tangent line. And again, horizontal tangent line means the slope is 0, or in other words, the first derivative at that point is equal to 0. All right, so this is graphically representing the second derivative test. That's pretty much the concepts. And the main point is that the second derivative test is a separate test that you can use to find relative min and relative max. And it's based entirely on the concavity of the graph. All right, and for concavity, if it's a positive second derivative, then that means it's going to be concave up. If it's a negative second derivative, that means it's concave down. All right, so these are the concepts for the section. So the next video will be examples. And by examples, we'll find the first concept was concavity. So we'll find what intervals of concavity. And then we'll determine inflection points. And again, inflection points are points in which the graph switches concavity. That's separate from the second derivative test. All right, second derivative test only is dealing with relative min and relative max. That is not the same thing as inflection point. All right, so inflection points, we'll be determining that for some examples, like here, the point where it's switching from concave up to concave down. And then last, we'll be dealing with examples where we will apply the second derivative test, which is a separate thing from inflection point, determining where these relative min and maxes occur. All right, so that's it for this video.